Well, then I would now first thank Professor Anderson for his nice words and his opening address, and then invite and introduce first Geoffrey West, who is a distinguished professor at Santa Fe. I heard Geoffrey speak for the first time in March 2004 at a meeting of the Complexity Research Group at the London School of Economics. That was a remarkable meeting because its key speakers were some of the big shots in the area of interdisciplinarity and complexity, like Brian Arthur, and Robert Axel, I think, was there as well. It's quite a few people, and Geoffrey West. The title of his talk at that time was The Complexity, Unity, and Simplicity of Living Things. I talked with Geoffrey for the first time in February 2006, because I didn't talk to him at the London School of Economics. About half a year after he had become the president of the Santa Fe Institute, I had just started with the Institute Paralimes and carried officially the title of president of the Institute. So we were colleagues. That meant that our metabolic processes were basically the same. However, in terms of scaling, Geoffrey was the elephant and I was the mouse. It was the first of many discussions I had with Geoffrey on complexity and interdisciplinary science, on running an institute like SFI, and on cooperation. The characteristic approach of Geoffrey towards cooperation was cooperation, exchange of people, joint programs, joint workshops, yes, 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 and yes. But there's one caveat. It must be driven by the scientist. Later, when NTU had set on its course towards a complexity program, Geoffrey played a key role in spreading the virus of complexity and interdisciplinary science. And so it is with great respect and pleasure that I introduce Geoffrey to talk to us.
I don't have a mic, right?
Take this one.
Can everybody hear me? Can everybody hear me? No. Can everybody hear me? I'll try to speak loud. This doesn't seem to be working.
It does not work?
No. Hello? 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 Is that better? So, yeah, thank you for the introduction, and it's a great pleasure to be here and to see new faces and be reacquainted with old friends. And I feel just a tiny bit intimidated because I was given the task of giving kind of a big, broad overview, an introductory overview of complexity and what I like to call transdisciplinary science, and recognize that I'm talking to an audience, some of whom are great experts in some of the things that I will touch upon, and some maybe this is their first exposure to some of these ideas and this way of thinking. So you'll have to bear with me in terms of the talk being, first of all, very purposely at a very simple level, even though it's talking about complex things, and it's going to be highly non-technical. And if we want to go into anything more technical or into any of the background, we have lots of time after I finish the more formal part of the presentation. So here's the title. And it has this curious kind of question mark in parentheses, because the original title of the talk that I taught was the declarative version of this, no question mark, namely complexity and transdisciplinarity. It is a science for the 21st century, which is what I personally believe, and probably, well, in fact, Berkel basically said it in his introductory talk. But it's a question, it is a question, and part of that question is to do, can we in fact make it into a serious science? And I'm not going to be able to answer that question, but it is implicit in everything I'm going to say. So I'll begin with this famous quote that I noticed was actually in the book. This famous quote from an interview from the San Jose Mercury in the year 2000, in which Stephen Hawking was asked whether the 21st century was going to be the century of biology, and he said, no, it's actually going to be the century of complexity. So he buys into the declarative version of this. But of course it begs the big question, what the hell do we mean by complexity? And I won't dwell on this too much, but I will talk about it a little bit. But I use something I used, it may have been the first time I talked at NTU about complexity. In fact, I'm pretty sure it is actually. And it was using this famous quote, he's famous in the United States, by a distinguished member of the United States Supreme Court 40-odd years ago, discussing the problem of pornography. And the problem there was free speech versus the questions of protection of the social fabric. And one of the major questions that the Supreme Court had to discuss was the definition of pornography. And Potter Stewart made this wonderful comment, I shall not today attempt further to define pornography, and perhaps I could never succeed in intelligently doing so, but I know it when I see it. And what I did 2 or 3 years ago when I talked here is okay, so, you know, and many of us believe that. I mean, that's, you know, at least that's the way we behave. We know it when we see it, and many of the examples that we talked about, we recognize it as such. So what I'm going to do to begin this kind of introductory overview is first talk about something else that we recognize, but it's not usually thought of in those terms, and that is simplicity. So this is a system which we're all familiar with, and this is a simple system, meaning the motion of the planets around the sun, or, I don't have my iPhone with me, the fact that, you know, my iPhone works. If I call Bertel, after all, the thing goes up to some satellite and comes back down here right now. And the reason that can all work is that we understand the physics and mathematics of this to an extraordinary degree of accuracy. And in fact, in terms of the motions of the planets, a couple of small caveats maybe, that system we described just by 2 equations. Newton's laws of motion, second law of motion, and Newton's law of gravitation. If you solve those, you solve the motion of satellites. And, you know, there are corrections you have to put in and so on. But basically, this, in a certain sense, defines a simple system. Some very complicated, so it's complicated, it may not be complex, it's complicated in terms of actually solving those equations to get the degree of accuracy we want. But it can be encoded in something extraordinarily simple. The crowning glory of that, of simplicity, which is really the stuff of physics, is one of the great achievements of the second half of the 20th century, the understanding of the interaction of matter with electromagnetism, which is chemistry. It's chemistry, matter, and so on. All encoded in, that's a Lagrangian, we don't go into any technicalities, but encoded in some simple equation giving rise to a methodology and a very complicated but simple, because it can be encoded in a simple equation, complicated algorithms for making calculations. So much so that this theory predicts the strength of the magnetic moment of the electron to more than 12 decimal places. It's one of the great achievements of this calculational endeavor. And this, when compared to experiment, it's one of the most accurate experiments ever done, is the experiment of measuring the magnetic moment of the electron down beyond 12 significant figures. And you can see the agreement is remarkable. So this is the quintessential simplicity. Highly complicated, but encoded in simple equations, but in some paradigmatic way, the idea that you can make calculations to any degree of accuracy. Okay, whoops. So much so that, you know, what people call the theory of everything, string theory and so on, has the same kind of characteristics. So it's kind of weird in a way. A theory of everything, and theory maybe of the Big Bang and the evolution of the universe, is simple. But the things that are around us, the problems we're dealing with, have a very different characteristic, and I now want to move into that by going back to our picture of the solar system. Because when we wrote those equations and we said we could solve it to any degree of accuracy, we assumed, of course, that the structure that you see here, the rings of Saturn and the striations on Jupiter, and the junk floating around on the surface of the Earth, these don't play any role. That is, in those equations, we don't care that Mars is red and that the Earth has a structure on it. And what you recognize immediately is that if you had a different resolution, so the resolution in which we think of it as a solar system, when we have a resolution where we look at the planet Earth, we see extraordinary structure, and we see a bunch of interactions. Maybe that too could be somehow understood. But we see this extraordinary structure anywhere we look. And if we go to a deeper resolution, we see things like this, which we're all familiar with. This is the stuff of complexity. This, you cannot write one equation, or two equations, or three equations, or 10 equations, or a million equations to describe everything that's going on in here. Meaning, the entire structure of this forest, its evolution, its growth, the multiple activities that are happening, there we need something else. And I'm going to come back to this because we're going to discuss in what way maybe we can make this into a quantitative science. This too, urbanisation was mentioned. Can we make a science of this? And in fact, we could also ask the question in that context, is that actually just another version of this? Or is it something completely different? Is there a different dynamic? So already, may I say, thinking in these terms brings up different kinds of questions. So, if you start thinking of these systems, we already recognize that the usual characteristics that we think of physical systems, like energy, temperature, entropy, and so on, enter, but they enter in different ways when we think of these in trying to make a systematic science of trying to understand them that is also predictive. So here, we'd like to understand this kind of phenomenon, this kind of phenomenon, and this brings in already something that is going to be a theme throughout the rest of what I'm going to say, something we've recognized. This is a network. This has network characteristics, the obvious one being the things that you see, but this also has built into it all kinds of other networks that you can't see, because there were networks of people that not only interact on the physical networks, but those networks were required in order for this to be constructed in the first place and to be maintained. So we need to talk about that a little bit. And of course, they're all driven, as I say, by energy, and they couple into, of course, the entire cycle, the carbon cycle, the energy cycle of the Earth. We need to understand that if we understand these systems. So we're getting the sense that these systems also are not independent systems, but are coupled, highly coupled systems. And of course, those systems, when we're thinking of cities and social phenomena, produce goods, and understanding where these goods come from, the kind of networks that underlie the production of those goods, the distribution of those goods, and how that interfaces with the economy, with the ever-growing economy. And we understand how all of that acts in a kind of systemic way in this highly coupled kind of interacting system. And then looking at this and asking, how can it be that you can have a system, if you're thinking in more physical terms, that is forever growing, which is what our whole economy is based on. How can we have a system that is forever effectively exponentially increasing? And is there any structure to this that is that we can put into mathematical terms? And I will return to this also a little bit later. Okay. And of course, that economic activity, it's just repeating roughly what I was saying, leads to this idea of ever open, expanding growth. And therefore, into the biggest question, is any of this actually sustainable? So is it sustainable on a local level, but is it also sustainable on a global level? And this you can't read, but what this happens to be revenues for a bunch of software companies of Silicon Valley. And that's there. Plotted on the y-axis is the sales, and plotted on the x-axis is just time. So it just goes continually increasing. Is this kind of thing sustainable? So that's a big question. Well, if one is familiar with the second law of thermodynamics, and we have all of this stuff happening, all these wonderful things happening, all fueled by energy, necessarily there has to be entropy produced. And I would call that socioeconomic entropy because many complex systems are socioeconomic. So an inevitable outcome of all that has to be this, and this, and this, and this. I forget what comes next, and this, and this. So we'd like to understand. So this is very important to understand how these systems, which have enormous numbers of degrees of freedom, enormous number of actors playing within each system that you look at is highly coupled to another system, and so on. It looks kind of hopeless, and that's the challenge. Okay. Well, I said one of the hints that maybe we can start to address these questions comes from thinking of them in terms of, first of all, energy supplied like this, which are network systems. Like you and I are, we're network systems, and this is basically another version of, let's see, if I go the right way, this, oops, wrong way. I'm afraid my thing is going, okay, yeah, we'll go backwards. So, question is this as a network similar to this as a network? This, obviously part of the last one, and this, which is the internet. Okay, and you will hear Laszlo is here. I don't know what he's going to talk about, but you have maybe a leading person thinking about network structures and what we can learn from it, and start to address some of these questions. Okay, so these are the kinds of networks I'm actually much more interested in than some of those, really. And it's just, I put this diagram up simply to remind you that you are networks. And in fact, what this is the top thing. There is a genome network. The middle one is the metabolic network. So this is your informational network, if you like. This is your energy network, your metabolism. This is the network inside mitochondria. This is those little engines inside you which produce your energy. There's about 500 to 1,000 of those inside each cell. These are networks within cells. And this is the network, another network to do with information. That's your brain. That's the white gray matter, your brain. And this is you as an integrated whole. And all of this has to be extraordinarily integrated, but we're already seeing a certain commonality. There are networks, and networks are subject to interesting mathematical analysis. Okay. So one of the aspects of these networks, we go back, of these networks is that they have this kind of self-similar property, which we're very familiar with, namely that, just take this one, from here, if we cut here, this network looks like the whole thing. So that's self-similar and that's fractal. And this lovely example, again, I'm sure you're familiar with. There's a cauliflower, so kind of cauliflower, taken at various resolutions. It's just very different resolutions, but it looks the same, basically. You cut off a piece of this, it looks like the thing as a whole, and this photograph is trying to emphasize it. So this fractal-like behavior seems to play a role across many, many dimensions of complex systems. And one of the interesting questions is, what are the principles, the underlying principles that are driving that and leading to that? What kind of optimization, if it is optimization, is taking place that we have these kinds of systems? Well, we've already mentioned the brain, and it was mentioned this morning before me, and the cell. These are obvious complex systems that have these kinds of interesting challenges, and these are, obviously major foci for starting to think about understanding how these systems work and so forth. Now, the origins of complexity, people thinking about complexity, actually predate the more modern focus on, or maybe they're unparalleled in some ways, the more modern focus on socioeconomic and biomedical kinds of questions. And the earliest work is really to do with nonlinear dynamics and questions of turbulence. This is a wonderful picture of the turbulence being created by a small aircraft putting pesticides on crops. But you see these beautiful patterns, beautiful turbulent patterns. And this was this is manifestation of highly nonlinear kinds of behavior. And I wanted to show you, and I've never done this I've never done. I'm going to show you a video, which I hope this works. And you'll reckon, oh, shit, here we go. Yes, there it is, Jupiter. Okay, can you see it? So there you see it's weather. We're talking about weather. This happens to be Jupiter. And what you see, what is very important, is that what you see here as the things like the red spot, even though these equations are highly nonlinear and there's an extraordinary amount of complexity, there is an extraordinary invariance. This red spot has remained incredibly resilient over an extraordinarily long periods of time. So that there are, despite this complexity and so forth, there are invariants, and namely things that remain pretty much fixed over long periods of time. So that was one kind of idea that started to develop in mathematical physics, and the other is this one, which is not complexity, and many of you have seen this too, but it's always fun to watch, and it's the metronome problem. Let's look at yes, the synchronization of metronomes. This is actually not a complex system. You see what it is? It's everybody's seen, I'm sure most of you have seen this, bunch of metronomes just arbitrarily rocking back and forth, and so totally random. And now, put on top of a couple of Coke cans so that there's a small interaction between them. And watch, if you haven't seen this. Okay. So suddenly we all vote for George Bush. Again, this is it. Now keep watching. This is actually a good video. It's too long, this, but I'm going to take a minute or so before, so you just watch it. Because the guy that made it moved that cursor off. So there it is, nice, all in synchrony, and so forth. All because they're interacting with each other, of course, now because of the connection through the coat cannons. Tiny interaction between them. Now what he does, he removes it. No longer an interaction. Watch. There comes decoherence again. Individuals emerge. I think this will play into Louise's point, I hope, about individuals like this. So no longer do we have a collective motion, we have an individual motion. So this is actually not complexity, but it is a wonderful image and metaphor for the kinds of phenomena we see in complex systems. Okay. So, just to give the first summary, here's just a laundry list of a whole bunch of characteristics of complex systems, and I'm just going to read through them, just so that we're all on the same page. And it's not exhaustive by any means. So there are a huge number of actors, 10 to the 14th cells in a body, 35 million people in Tokyo, huge numbers of individual actors, but there are multiple scales to the problem. Many different scales, both in space and time. So if you look at a city, you can either look at an individual house, you can look at a whole neighborhood, you look at the whole city, but there are different coherent effects, and that last film was an example of trying to illustrate coherence that can occur, coupling that can occur, because these systems typically are strongly coupled. That one wasn't, but they're strongly interrelated, and they are almost always non-linear. There's a non-linear reaction to an effect. The other thing, which is I was going to mention when I showed you the aircraft dusting crops, the chaotic phenomena, that is sensitivity to boundary conditions. So complexity can have either something like the Jupiter red spot, even though it has all these properties, it is there's a stability and resilience in the system, but it can also be extraordinarily sensitive to small changes that propagate through the system. And the classic, the image of the butterfly flapping its wings in Brazil creates a hurricane in Florida a month later. That kind of image, and indeed maybe the subprime mortgage problem in the United States, which is a minuscule part of the total economy, maybe the perturbation due to that is something that we thought of as chaotic, bringing down the economies of Greece, maybe Portugal, Ireland, maybe even the United States. So this is at a minimum, it's a great metaphor, and maybe there is even some serious mathematical framework one can erect for understanding that. These have emergent phenomena, namely, the whole is much more than the sum of its parts. This is classic in all these complex systems, and different phases of the system and so forth. So going to our body, obviously, we are more than just the sum of 10 to the 14th cells, but much, much more. So these emerge as we change scale, and that also leads to this really challenging problem that if we want to understand the system and make predictive statements, we run into problems of unintended consequences intimately related to that chaotic phenomenon. Things that are very difficult, if not sometimes in principle impossible to predict. These systems are typically adaptive and evolving. They are I'll use the word Darwinian, but they are adaptive and evolving, and that in fact also relates very strongly to their potential for being resilient, and that adaptive evolutionary characteristic, of course, is another way of saying it, is that the system now depends upon its history. That is, the way it is now is often historically contingent. If you think of Singapore, Singapore could have ended up being presumably just a small town, a small port as part of what is called Malaysia, if the history of the British Empire, and I don't know enough about it, but obviously could have been different, and various historical events has caused this extraordinary city-state to emerge, but you could have imagined maybe another set of circumstances where it's just been a small port part of another country. So there's historical contingency and path dependence, and something I haven't emphasized, these systems are typically way out of equilibrium like we are. They're not thermodynamic equilibrium. And the two things I want to emphasize at the end here, which I've already implied, and that is, for complexity science to be a science, we have to be searching for the potential of underlying simplicity. Is there an underlying simplicity? Or is it just a great big mess, and each problem that you look at has to be dealt with in its own terms? Or are there some transcendent universal principles? So that's the challenge of making a complexity science. And one piece of that, which I have mentioned, is the difference between being complicated and complex. And I think that's the next one. Oh, no, I'll come back to it. So I talked about that in terms of the solar system is very complicated, but it's not complex. So there have been all kinds of ideas floating around, and people have worked very hard on, and there are people in this room that have worked very hard on them and have developed them. We've talked about nonlinear dynamics, which came out of mathematics and physics. But one of the great advances in coming to terms with complex adaptive systems was the tremendous advance in computation. So that was the real change. Prior to that, it was thinking about things like those turbulent phenomena and the coupled pendulums and so on. But the development of powerful computation meant that you could simulate these systems, and the great discovery, which many people have already thought must be true, is that underlying complexity is a potential simplicity, because you could make very, very simple algorithms for a system and let it evolve, and extraordinary complex behaviors would emerge that are quite similar to the ones that we see in the real world in terms of their characteristics. So this gave credence to the idea that, gee whiz, underlying these what looks like a complete mess actually are very simple rules of work from these simulations, and our job as scientists is to reveal those rules or principles and then start to put together a serious science of complexity that can be applied across a broad spectrum of problems. And that does bring up the question, is there such a theory? Is there kind of a universal theory of complexity, like there is a universal theory of thermodynamics, system mechanics, and information? Namely, if you recall, thermodynamics came about originally, people trying to understand steam engines, how engines worked, and how could you make the most efficient engine? And out of that came Clausius and ultimately the second law of thermodynamics and so forth. And so the question is there anything analogous to that in terms of a theory of complexity? My own, whatever it's worth, I don't think so. But I did write down, just to remind you, I'm not sure this is very meaningful, but I wrote down, just to remind you, the second law of thermodynamics and its relationship to underlying statistical mechanics through the famous formula P log P, and the transition of that to information theory, which I'm not going to talk about very much, but I would say one of the truly major challenges of 21st century science, and very much as part of the rubric of complexity, is to come to terms with the interface and integration of energy and resources, in biological terms, metabolism, with information, in biological terms, genomics. That is, how in all these systems does the energy networks and informational networks interface and integrate. Just an editorial comment. One of the big problems, to my mind, in biomedicine is that this totally dominates the thinking, and that's dangerous. And in fact, it was obviously ridiculous, the idea that the human genome, this is editorial, the human genome, discovering everything about the human genome would solve all diseases. This was ludicrous ab initio, but it was stated, and there are still a few people that might even believe it. Why? At a minimum, this has to come in because this actually is the basis of life, is energy. Without energy, you wouldn't have information transference and so on. So you need that, and then you need the interface with the environment, and it is a complex adaptive system, and that's what we need to come to terms with. Okay, onward. So here it is. Just to repeat, this is what we want. We want the search for underlying laws and principles leading to a quantitative, predictive, conceptual framework. And I've already effectively asked the question, can there be a Newton's laws of complexity? Complex adaptive system. When I wrote this, I put a big no next to it, which is true. There can't be, I believe. Meaning, in the same sense that we have Newton's laws of motion that tell you the motion of those planets to any degree of accuracy, or quantum electrodynamics that tells you the magnetic moment of the electron to better than parts per trillion. No, obviously not. However, maybe we can have a theoretical framework that allows for coarse-grained answers. So let me now explore that. And I'm going to do it by putting up some examples that we already, some of us are familiar with, some of you are familiar with some of these, namely the kinetic theory. Most of you are familiar with the kinetic theory, developed in the 19th century by Maxwell, Boltzmann, and so on. So you remember, that theory said the gas in this room is made of little billiard balls that collide elastically. Ludicrous, completely wrong. Was actually, they knew it was wrong. But let's see what happens. And out of that came some remarkable results. In fact, you could say statistical mechanics came from that, and all the modern theories of condensed matter came from that kind of thing. And of course, it had to be amended with quantum mechanics and so on and so forth. But it was a coarse-grained theory because it gave rise to understand the ideal gas law. It made the extraordinary prediction, which Maxwell was vilified, that the viscosity of a gas is independent of its pressure. Totally non-intuitive, turned out to be right. And incidentally, Maxwell did the experiment, so everybody thought it was ridiculous, it couldn't be right. The quark model of elementary particles, your quarks, these little elementary particles that just buzz around and so on, was wrong, but it gave rise to extraordinary progress, and ultimately to a complete theory, quantum thermodynamics, which is a real theory integrating strong interactions, exponentialism, and relativity, and so on. So these are examples we've had in terms of a way of starting to think about these and willing to take a risk in making some big assumptions in order to start to develop a serious theory. Okay, just as in physics, that is typically called a toy model, and the word toy there is in no way pejorative, quite the contrary. So the one that I got interested in is the last one, longevity. Why is it that I can whimsically say with absolute certainty that everybody in this room will be dead in 100 years. Okay. That's a prediction, it's a quantitative prediction. Where in the hell does that number come from? So that's the kind of question. So understanding aging, which is biologically a fascinating problem of itself, but is a crucial problem for human beings to understand. It's important just in general, but it's very important to understand the process of aging and its relationship to disease and decrepitude and mortality. So I'm just going to flash on 2 or 3 questions in this spirit to stimulate the kinds of things that have stimulated my own thinking, and one can take these into any area, of course. So there is it, that's what I just said. Why do we live a lot of 100 years? Why is it 100 years, not 1,000 years or 6 months? And how come a mouse, which is the same stuff, first approximate, is identical? This piece here, look, this thing here could have been a mouse, but it would have been dead 68 years ago. So how come? What's going on there? So where does this time scale come from? And most importantly, how in the hell does 100 years come from molecular time scales? Where does it come from in the time scales of the respiratory enzymes to control our production of energy, or in the molecules that are our genes? When I started looking, actually, just another editorial comment, reading about this, they would say, well, it's genetically programmed. Vacuous kind of statement. Well, not title, but it's vacuous in terms of being predictive. You have a theory. So where is it? Those are genes and molecules. They have molecular time scales. How in the hell do those genes know, if that's what it is, that 100 years, if you're a human being, you're all going to be dead, and if you're all mice, you've been dead a long, long time ago. So that's a coarse-grained question, because you could imagine a complete theory of aging, mechanistic theory, that takes into account much of the dynamics of living, of metabolism, and how that degrades, so questions of wear and tear, and the thermodynamics of that, the networks that are supplying it, and the way they erode, and so forth. One could imagine such a theory for answering these questions, but they couldn't say how long birth was going to live. Okay. So it's in that sense, it's a coarse-grained question. Similarly, why do we have to sleep 8 hours? Why not 1 hour, 10 minutes, 23 hours? Where does 8 hours come from, and why? Why do mice have so many more tumors than human beings per gram of tissue? Whales have almost none. That's true. Then why in the hell do we spend so much money working on mice? Why should we believe any of that stuff? NIH spends billions, has spent. Why should we believe it? Well, we need to understand that. Okay? I'm not questioning we shouldn't believe it, actually. I'm simply saying we need to think through some of those questions in these terms. Oh, and the last one, yes, of course. If you have a theory of tumors, which means growing something inside you when you're mature, so you have a network system that is mature and resilient for 100 years, and somewhere along that you grow something inside you, why is it sometimes good and sometimes bad? What's determined? What are the determinants of that? Why is it good to grow babies, but bad to grow tumors? And to understand that in a mechanistic, scientific, quantitative, analytic framework. Okay. Here's others that have stimulated some of our work, and this, I'm not going to talk about this hardly at all, because there's this little workshop on Thursday that we on cities. But similar, if you're trying to develop a theory of cities and companies, are they like biology? They metabolize, they age, they die, they can sleep, etc. And in fact, in terms of death, why is it that cities, very hard to kill a city? Because you can drop an atom bomb, not so far from here, an atom bomb's been dropped on cities, but they're flourishing now. You drop an atom bomb on Microsoft, I doubt that it will be in existence for much longer. But in fact, if I had time, I would show you the mortality curve. Businesses all die, all companies die. So a serious theory, if you had a theory, if there is such a theory, of the complex adaptive system called companies, might be able to predict when Google and Microsoft are going to go bust. So, I'm going to finish off soon. What I'm going to do, one of the things that I talked to Jan about was this kind of simple elementary talk, but then talk a teeny bit about the Santa Fe Institute. But I'm going to show you this actually, no, I'm not going to show you, I'm going to miss this out. I'm going to go, I will say this only about going back to this picture. So some of the work that some of us have been involved in was in fact taking this way of thinking to this very system I showed earlier and developing a theory which is actually based on some of the things I talked about, thinking of each tree as a network, the whole system as a network, the flows and the underlying principles that are constraining that system, and put it into mathematical terms, and to be able to answer how many trees are there of this size, how much energy is flowing in each branch, how many leaves does each branch have, how big is the canopy, etc. And developing that theory, and I think the next slide, yes, I showed this one because it's next door, namely, this is the prediction, one of the predictions out of a theory of this complex adaptive system, and doing the complicated mathematics leads to a very simple prediction that the number of trees of a given size just goes inversely as the square of the diameter of the tree trunk. It's very simple. And here's data from a couple of, from Malaysian forests up the road here, and we have lots of data from around the world. This law is valid across the globe, all forests we've looked at. But you notice here, it's also valid over time, that this is a tropical rainforest, and the individual, in 1947, there were different individuals in 1981, but it satisfies the same rule. And in fact, this is not the place to show you any more data than this, other than one other thing I will show you, which is taking that, and now we're getting a little bit impinging on the practical, and asking the question, if we take that, and we couple it into the environment, how much energy is needed, how much energy is coming in from the sun, how much rain is falling, what is the ambient temperature. You can determine the nature of how the forest changes, the overall scale of the forest changes as you go across the globe, actually. And here we did it for the United States, and I forget which is which, but one of these is the prediction of the tallest tree at that spot in the United States, and the other one is the data. So you see it's pretty good. And this is very important in terms of questions of global warming and changes in the environment. Okay. So here's the idea. You want to try to understand that, and this is what you're doing. This is the lens, and this is slightly misleading because it's written down all the multiple equations that come in. They have to be integrated in some way, in some extraordinary way, and that's what that work is about, but it's not all these equations. This is a cartoon version of it, but just to give you an image. Okay, I'm going to finish up by talking a little bit about the Santa Fe Institute, and you already heard. This is an old slide, and I'm going to confess something here. I was president until, what was it, 2 years ago? I forget, 2, 3 years ago. And I had talks, of course, I had to give to raise money for the Institute, to present the Institute. And I've actually used slides from that. So nothing changes in terms of the message. It changes in terms of things like, you notice this says 25 years, and it's actually, I think you said 28, whatever it is anyway, but that's just a side comment. So it was founded by a group of very distinguished scientists, including these three Nobel Prize winners. And it was founded, as Berkel so eloquently said, out of a certain frustration that many of big questions, and especially those that transcend the disciplines, were somehow being ignored or swept under the rug. That more and more the reward system, whether it be for getting a job, or getting tenure, or getting a bigger salary, getting a grant, doesn't matter what it was, the reward system more and more was becoming more and more highly focused and stovepipe. And so, and in fact, it wasn't only that it was stovepipe within a discipline, but what was beginning to evolve, and has now gone to that stage where, at least in many major universities, many major US universities especially, if you talk about the physics department as a singular department, it's very misleading. It's actually 5 essentially semi-autonomous departments acting almost independently. It's not quite true, but it's almost that. And so this is a very serious problem in terms of both the psychology of young people, especially interested in bigger questions that transcend the narrow boundaries of their sub-discipline. But I think it actually has a urgency and a bit of a crisis aspect to it in terms of the multiple questions we have to face as a society, both either locally or globally, in terms of environment, health, crime, finance, risk, and so forth. All of these questions we have to come to terms with as complex adaptive systems, and systemically as a complete complex adaptive system. So that was the kind of framework in the background, and these people felt, and incidentally I said young people, but in fact, these 3 people, even though they had, here, I'm in one company here to say that they had real Nobel Prizes. You know, they're the #1, in my opinion. These are outstanding scientists who, of course, no problem getting money to support their research. But if Murray Gell-Mann was interested in the origin of language, as a complex system, or Phil Anderson was interested in economics in terms of statistical mechanics, likewise Ken Arrow, they felt that they were being somehow written off by their colleagues. They're turning into, old men that are no longer serious scientists, because they're only interested in trying to understand all of economics. That's, that kind of thing. So this was a serious issue, and they felt there needed to be one place on the academic landscape where the opposite was true. That instead of things being stovepipe, it needed to be a place where scholars came together with different backgrounds, different ideas, more speculative maybe, but wanting to bridge the divides between disciplines and bring their techniques, way of thinking, their paradigms to it together in a collegial fashion. And they founded the Santa Fe Institute as an experiment. And I would say it's been an ongoing experiment since then that I would say by almost any standards has been a success, but it's still an experiment, I would say. And I'm just going to say, I've put this up because this is the first serious program, major program. And Brian joined it. You probably were already part of this at the time.
I ran it. That
Yeah, you managed it exactly. So, and this is from Science magazine, 1989. And the reason I'm showing you, and what it was this combination of physicists and economists was the idea. And Science wrote it up in a curious way. They said, an unlikely liaison, first of all. They talked about it as an unusual collaboration. Although the project may seem somewhat quixotic and so on, because it was so unusual at the time. It was so, and of course, the outcome of this, regardless of what impact it's had on economics, has brought together these fields, and for good or bad, has brought mathematics and physics onto Wall Street. a certain sense. This is, I would say, is really the germ that created that. But it's extraordinary, but it did set the tone for this kind of collaborative effort and people reaching across. Okay, so here's the structure of the Stanford Institute. You've got to remember, and I think if there's a discussion afterwards, the major issue for taking these ideas is now, it's what I'm going to be talking about now, because the Santa Fe Institute was set up outside of the universities. It was part of the university system, it was part of the academic landscape, but it was not part of another institution. They made this extraordinarily bold move of making it independent and with it not under the umbrella of something else. And in fact, as I understand it at the beginning, it was very natural, and in fact there was a lot of talk of making it part of the University of California, because a lot of this came out of Los Alamos, and that would have been very simple, very easy. And I think they had some extraordinary foresight, and this is the big warning sign here, that if you become part of a university, especially at that time when it was new, it would be great the first 2 or 3 years, and then it would regress, in quotes, being just like every other part of the university, and you lose the goose that lays the golden egg. So they made this very strong, bold move that it will be independent. And that meant the question which I will talk about in a moment about how does it get supported that way, and indeed what is the best structure. So the structure that has evolved, and this has been discussed many times by the SFI community, is the size of it. And this represents a size, it's now smaller than this, and it's smaller than this because of the 2008 market crash. That our funding, and I'll talk about the funding in a second, became, we had to retract, and so the numbers are now down from this, but it gives you a sense of scale. So here it is, it has maybe the order of 15 resident faculty, half of which are actually only there half of the time, maybe. It has, we try to have a large number of postdocs. We have lots of visitors. There's a huge flux of visitors, there's lots of talks. There were the numbers that this number represent at that time was between 300 and 400 visitors a year of different kinds. There were lots of working groups. There were lots of workshops. We do actually less workshops now. And we've had quite a big impact. But one of the most important things is the thing of the number at the top of about 100 external faculty. And some of the people here, there's a big part of the SFI. It's very interesting. Steve Lansing and Brian Arthur, who will talk here, both were at one stage resident faculty. No, you weren't resident. You were sabbatical for a year. Sander was sabbatical. But all three there, and maybe others, are external faculty. And the idea is, and it's a huge challenge, that they have the same rights and responsibilities as the resident faculty and are integral to the community. And getting that to work is a continuous challenge. Okay, let me move on with this quickly. So there's just the saying, I'll skip this. This is just putting it as a laundry list of numbers. So it has been recognized as the birthplace of this kind of work, both in many, many places. And I'm going to, I took some slides to toot our horn. And part of this, so I'm going to show you some very nice things that have been said about the Santa Fe Institute. Part of this is because I'm proud of the Santa Fe Institute and I love it. And I had to say this seriously at some stage, but part of it for here is to recognize that what you said, there is an extraordinary opportunity. There's no reason that you can't have the same visibility and the same impact. And I want to just plant that. Okay. So I'm going to skip over this very quickly, but these are just some of the generic characteristics of SFI science. And I'm not going to read them. You can just glance across them. I just want to leave you with an impressionistic view, but these are some of the things that I've already said in my words earlier, and these are, again, just a continuation of some of the questions. Some are very academic, and some are fundamental. As you can see here, and some are a little bit way out. Are there laws of history? What part of history could you think of as science in any way? Is there any? So we've had a couple of workshops on that. But that's a far out one. But, you know, then there's all kinds of questions about, which I've already referred to in a way, cancer, sleep, aging, mortality, designing vaccines. Based on evolutionary biology is a program at the Science Institute. Okay. Let me skip this. Lots of different collaborations among different kinds of people, physicists and economists, which we mentioned, but biologists, chemists, and so forth. So it's bringing them all together, paleobiologists, biologists, and physicists on ideas of innovation, so we get to develop the science of innovation. Something that Brian has been very heavily involved in, and so on. So I'm not going to, as I say, I'm not going to dwell on these. I'm just flashing them on to give you some sense of the breadth and of some of the programs and things that are going on. I'm going to skip these. Again, this is just from the multiple publications that have come from it. Again, to just give you this impressionistic view. This is a big program, The Origins of Human Altruism. Its relationship to evolutionary biology and natural selection. This was work on it was called Culture Crash, again, because of the economists and physicists working together, but trying to understand crashes. And here was some work by one of our external faculty, John Rundle, on taking ideas of earthquakes into market crashes. Is there something? Some of the ideas of the mathematics developed there to understand market crashes and so on, origins of life and so on. And this was trying to understand, there has been on and off quite an aggressive program trying to understand information networks, and particularly how they relate to computer design. And related to that, malware. How do you deal with malware? And you see malware in a similar way to you see viruses. So we had actually one of the most interesting workshops I attended at SFI was one where it was brought together many of the major software writers from Silicon Valley, from Yahoo, Google, eBay, and so on, top people, with a bunch of evolutionary biologists who would think about the evolution of viruses and the spread of disease. That was absolutely fascinating, actually. And some good things actually came out of that. This is understanding conflict. Is there a science of conflict? Here's something that, I don't know, Laszlo must have worked on this too, I'm assuming. The dynamics of terrorist groups, thinking of them as networks, looking for the nodes and the hubs, the links that are vulnerable and so on. So, okay, let me skip this, and I'm going to skip this, skip this. This is what I like. And now I'm going to skip this because I'm going to spend too much time. Social networks. Now I want to talk a teeny bit, I'll finish up, about our successes. So, this is an old one. In 2007, we had two pieces of work made the greatest ideas of the year in Harvard Business Review, which was a great compliment, and we've done rather well with them over the years. Our citations continue to increase exponentially. This was an old one, and it stopped because that was, as it says there, that just goes through 3/4 of the year, but it's continued that way. But this is the most important one in some ways, because when I was president, I was always challenged about impact. You show us real impact. So these were the numbers at that stage of the number of papers in Science and Nature with SFI byline. Okay, so that does include the external faculty and so on, but it shows you the impact of the connectivity coming from the Institute, and you can see it's risen to about 20 And of course, the fundamental question here is 20 a tiny number? Not very many complications, 20. Or is it a big number? I don't know if anyone knows. This is actually a huge number. This is an enormous number because if you look at this, the numbers in that same year, 2008, for major universities, you can see, except for Harvard and maybe Stanford, they're all in the 40s, 50s, 60s. And our budget at that time was $11 million. And the research budget of each one of these universities is over $1 billion. So per paper, this was the point, per paper, we're almost 2 orders of magnitude more productive. So that was the big pitch. Okay, oh, there's British ones, because they talk in English. Okay, so there's been lots of good things happen, and you can see the kinds of things that result from this. I won't read them, you can just see them. And you're one of them. I didn't write this down, but you see paralemus, imitations is a serious form of flattery. Lots of places have tried to copy. It is a huge problem as to take this and plant it somewhere else. I'll skip that. Lots of books, lots of good things. Some of the people here have written some of these books. I'll skip this. Lots of wonderful things been said. The only one I will point to is this one. This was a report to the National Science Board, which oversees our National Science Foundation, and it was about, actually they were dealing with what transformative science, actually, and they were asked, Rogers Hollingsworth is at the University of Wisconsin, he's famous for looking at how ideas develop within institutions. If you get a Nobel Prize, how did that come about? What was the dynamics that led to it? And he made this wonderful remark. My colleagues and I have studied approximately 175 research organizations on both sides of the Atlantic, and in many respects, the Center Institute is an ideal type of organization which facilitates creative thinking. That can be interpreted in many ways, but it's a good statement. Okay, I will miss this out. And lastly, lots of media things. 2 last things. We have a big business network, or at least we try to have a big business network. We think it's extremely important that the business community be an integral part of this. So we have these companies at that time. It changes, of course, but having these companies as part of the network, it's a different network than the academic one, but they interface with symposia and workshops and so on. So we do that. We hold workshops, for example, not just in Santa Fe, in Chicago, in New York, San Francisco, and so on, with the business network. Let's see, we have an educational program I want to talk about, and this is important. We have summer schools, and I think that's very important, and I think that's a crucial thing, and I think NTU can play a very important role in holding such things, of course, in Asia. I'll skip this, and I'm just going to finish with 2 quotes that I like to quote. One is this famous one from Max Planck, because this is a shift. In much of this thinking, it is a shift. And I think this is an important statement about changing the way of thinking. Changing the way of thinking. It actually rarely happens, as he says, that Saul becomes Paul, that people actually get converted. It's a rare occurrence that senior people, established people get converted. It's what you have to do is wait for young people to come up. So young people are crucial. That's why having lots of postdocs and students are critical. And the last thing, I used to show this every single board meeting. So our board of trustees met twice a year, and I showed this quote every single time. It's a quote about the death of Max Perutz, who was famous for he got his Nobel Prize for hemoglobin, the structure of hemoglobin. And he ran, I forget what it's called, I forget what it's called, the Medical Research Council Institute, or whatever, some weird name. But that was an extraordinary place, and he got, I forget what it says here, some huge number of Nobel Prizes, I forget 9 or 11, in a very short time. And here's what I want to read to you, because you probably can't read it. Impishly, whenever he was asked whether there are simple guidelines on which to organize research, So the highly creative, meaning produce lots of Nobel Prizes, he would say, remember, impishly, he would say, no politics, no committees, no reports, no referees, no interviews, just gifted, highly motivated people picked by a few men of good judgment. And as I said here, certainly not the way researchers usually run in our fuzzy democracy, but from a man of great gifts and extremely good judgment, such a reply is not illegal. So I show this because, not that you could do this, and I'm sure he can actually do it quite this way, but it is that, and I think to do a lot of this work, you need a highly enlightened leadership. And one of the things that attracted me to NTU, may I say, was Socioeconomic. I'd not say he would quite ascribe to this, but, and then Berkel. I think both are extraordinary in terms of their leadership qualities in recognizing some of the things that are said here. So it is the spirit of that, getting something going, setting it up, finding good people, and really giving them the resources and impetus to carry it out. And I think the time is very ripe globally, and it's particularly ripe within Asia for something like this. So I apologize when I'm way too long.
Thank you, Geoffrey, for a very nice talk. I should actually mention that Geoffrey arrived this morning by plane. So it's quite, apart from the fact that the talk itself is quite an accomplishment, to do that together with the jet lag that you had, it must have been quite an effort. Thanks a lot. We still have some time, and it is not often that you get a time to talk without limits almost, so you did now. I didn't have yes.
Well, I'm happy, no, I think it'd be a good time for questions and discussion and comments and criticism.
So, go ahead. Good.
Do you think there is an important distinction between non-living and living complex systems? And would you say that, for example, a city would be like a living system?
Well, I don't want to get into the question of the definition of life. You know, it's not quite as extreme as the definition of complexity. You know, in fact, I had a slide. Funny enough, I had actually in this talk a slide with addressing that in the sense of putting down, you know, about 10 characteristics of life, the obvious ones, you know, metabolism, reproduction, adaptation, etc. I forget that. Well, yeah, so, you know, a city in that sense is a living system. After all, a city is part of biology, came out of biology, which is like an anthill is in a certain sense part of biology, and I think a city is. But, and a city, because a city, what is implied in that question, if we're bringing up cities, what is implied in it is that cities are physical, just bricks and mortar and so on. But they're not. I mean, that's just the skeleton where the real aspect of the city is, namely what's going on here, us interacting and talking, trying to get ideas, innovating, dealing with problems, and so on. It's the people interacting in the socioeconomic aspect, which is kind of a virtual thing that is interplayed over the city, and that is one of the, so the city in that sense is a living system, and that also highlights this thing I put up on when we were talking about could there be a theory of complexity, that the challenge in those terms, in those kind of big fundamental terms, is the interface between the physicality of the system, which of course is energy, metabolism, second law, and so on, versus, or integrated with, the information that is being exchanged in order to, that gets expressed by ideas and you know, the evolution of economies and social behavior and so on. So that's kind of roundabout way. I haven't really answered your question, but that's my view.
Hello, Professor.
Please use the microphone. Okay.
Hi, Professor West. I'm from a group in the Philippines, a complex systems group under the National Institute of Physics from the Philippines. I would like to hear your view on the title of the conference, actually, More is Different. When do you think is many sufficient to be referred to as more? And whether there is a limiting value to this many such that if it becomes too large, the emergent property of a complex systems becomes suppressed. Because there's a very interesting idea about the concept of limiting value. We know in relativity that because of the limitation of the speed of light, it forces the time and space to be coupled somehow. And in the second part, more is different. What is the meaning of the word different in your opinion? You mentioned the whole is more than the sum of its parts, but can it be lesser than the sum of its parts? So these two words are quite tricky, and I think there is a very interesting philosophical thing that maybe we can develop if we want to quantify complex systems in a manner that can be addressed by physicists and natural scientists in general.
Well, I'm not going to answer your question. Well, I'm not going to answer the second part of the question. Maybe if I think about it, I could. But the more is different. I took to me what I said, actually. You know, the whole is greater than the sum of its parts. That there's, you know, and not only that it's different, but there are these emergent phenomena. I mean, there are emergent dynamics. There are emergent organizational principles and so on that occur at different scales. So that's what I took that to mean in terms of the, I don't remember, I read that article by Phil Anderson probably 20 years or so ago. I don't remember, I should have probably reread it for this. But that was my understanding of it, and it was just a kind of cute way of saying it. Less different, could less be, what was it, what would you say, could less?
We keep on saying that the whole is more than the sum of its parts, but can more be less?
Can more be less? Well, I
Can be,
I'm going to probably say
it is
something.
different, yeah, of course, but this different, can it be less?
I'll come back to that in a minute. I have an idea, but I think what the other thing you said, this thing about the limitations.
Limitation, yes.
Yeah, so I can address that a little bit, because one of the things in the work I was involved in was the question of what sets the, for example, I'll take a simple example. What sets the limit of scale of the size of mammals? Why is it that the smallest mammal is this big, and the biggest mammal is, you know, much, much bigger than this, as big as this building? Okay, what sets the limits? Why could you have had something smaller? Or why could you have had something much bigger than the whale? Or maybe there will be one day. Well, let's see. I'm not going to, I've spoken too long now. I'll talk about the big, maybe. And I'll give you a couple of examples. One is two speculations as to why you couldn't have, what sets the upper limit. One is, if you took a whale, first of all, if you stay on the ground, on the Earth, gravity, it turns out that, of course, you can't get too big because you just collapse under your own weight. So unless the only way you can make things bigger than a dinosaur on the planet is to evolve a species that can think and innovate and then use other materials. And that happened. Okay? That was the way natural selection dealt with land things being bigger than a dinosaur. So animals went to the ocean, so to speak, and they free themselves of gravity. Okay? So then what stops you? Well, the two possibilities there are, one, that it's so big, you have to eat, especially the way a whale is evolved, you have to eat almost continuously, and you have to be able to swim fast enough to get into areas where there's enough food. And there's obviously a limit to that. You know, there's a biomechanical limit. That's a possibility. So that's the coupling of the species to the environment. So that's one possibility. The other is So that's external. The other possibility is the internal one, which is the one I much prefer, and it's to do with the internal dynamics, and that is the following. That the animal, the mammal, is sustained entirely by networks, by energy, metabolites, and so forth, information, everything is sustained by networks. So it turns out, when you look at the mathematics of those networks, it turns out as you scale up, the distance between the capillaries, the endpoints of the network, systematically have to get bigger and bigger and bigger in a very, very slow way, extraordinarily slowly, slightly faster than a logarithm. It's actually a very small power law. And so and you sort of recognize that if you look at a big tree and you look at the top, the branches are slightly further apart than a small tree. And that's what's happening inside mammals as they get bigger. Well, that's in principle okay, but there's a problem. As you get further and further apart, you have to fill that space with cells that have to be fed. And it turns out you can't diffuse enough oxygen across more than about 2 cells. So there's a limit. You can't make this so far apart that you have 10 cells in between. This could not be sustained. And if you do that calculation, lo and behold, you find that a whale has to weigh, the largest mammal has to be of the order of 10 to the 8th grams, which is what a whale is. And there is another calculation you can do, which is to do with the efficiency of that network that starts to get, starts to decrease tremendously as you get too small, and that's because, and I will take 1 minute to say this, the wonder of us, of our system, our circuitry system, is that our tubes are big enough so that when blood goes down them and they hit a branch point, the wave, it's a wave, the wave goes down down one tube and then down the other, and of course if it's an arbitrary network it just reflects back too. Our tubing, our system, has evolved so that the size of those tubes, the relationship of the daughter tubes to the parent tube, is such that there is no reflection. That's classic impedance matching, which sends electricity across the countries. And that's how we've evolved. And it says the cross-section of the parent is the sum of the cross-sections of the daughter. And that's fantastic. And that's how all mammals operate in terms of their circuitry system. Now there's the problem. As you get smaller, those tubes, each tube gets smaller and smaller, and in particular your aorta gets so small that when your heart pumps, viscosity stops the pulse from transmitting down. Okay? So you don't have any longer a pulse. So it would be as if you had evolved or designed an animal that has a beating heart but no pulse. And it turns out, in that case, what you are doing is dissipating energy in every tube of your network, rather than what we do is we don't dissipate it until we get near the end of the network. It's an extraordinarily cleverly evolved system. And if you calculate, when you turn over, how small can you get before you've lost this pulsatile phenomenon? It turns out to be 2 grams, which is the weight. 2 grams, size of the shore. So, there are limits, but you have to work them out. It's not just as you do in relativity. You have to actually work it out. It's not a priori obvious. It is not a priori obvious that if you say the speed of light is a constant, that, that says there's a limit to how far something can go, but it doesn't say anything about masses and other characteristics. So you have to work it out. I'm not sure I've answered the question. It's kind of fun.
Okay. Well, it depends a little bit on the length of your answer, Geoffrey, how many more questions we can take. But I would say we have about 5 more minutes for some more questions, and so who can I...
I can see people.
So Geoffrey, two brief observations. You had the SFI Business Network up there. Having been involved in its founding, I urge the organizers here to do something similar, engage the business community of Singapore. I may be the only business person in the room, I'm not sure. But you skipped one slide which points to why that's actually a very important point. And that is your slide of an airplane components. And I'm an aeronautical engineer. And we are about to face a catastrophic, classic complexity catastrophe with the A380, an airplane designed on a computer, designed with materials that we don't understand very well, and the network of forces on that internal to that airplane are already producing cracks in the wings, which will soon make that airplane unflyable and will be an enormous business disaster. And you can predict the collapse of Airbus. And the end of the A380 coming fairly soon. The cracks have already started, and it may not be fixable because of the network of forces are not well understood. Us aeronautical engineers understood how to work in steel and aluminum by rules of thumb and breaking a lot of airplanes. We broke a lot before we figured that out. You couldn't break an A380. Unfortunately, during the tests, it broke at 1.2 load, and it's already experiencing 1.5 load. As a result, I wouldn't fly the A380, and Singapore Airlines may have a big disaster emerging in its hands. But these issues are practical, not merely abstract.
Absolutely, and that's why I had this slide up there. It was exactly that, so I'm very glad that you brought it up. Let me just, I'll take just 2 minutes quickly to answer this. I'm not answering, I'm agreeing with it. So in addition to all of that, what I was going to say, or some version of that. This is not the A380, this is the Boeing Dreamliner 787.
2 engines, not 4, big difference.
But here's the point I was going to make here, which is speculation. And we've talked to Boeing, Luis and I have some sort of collaboration going with them, and they do support some of this work. And probably, I don't know, I may be in trouble for saying this, because they've said it, some of them. So here's a speculation, you know, and it just provides, again, a way of thinking that is worth pursuing, I think, if you're a company like Boeing. So this is the Boeing 787, and it was the first plane that they built. First of all, it had, just as Peter said, like the 380, it had different engineering, different materials, and so forth. I won't go into that. But part of that meant that what they did is they globalized. And as you look at this, you can see where each piece is being built. And if you notice that only one piece is actually built in the state of Washington, which is where Boeing is, even though they assemble it there, which is not part of their long tradition. Their long tradition had been much of it to be much more centralized over the years. The other thing they did in terms of their business was to make each one of these companies, or at least the part of it that was dealing with this, kind of semi-autonomous. So it wasn't a subsidiary of Boeing, it was kind of semi-autonomous. And so what they had not realized, so put it in the language I introduced the talk in, Boeing, with all due respect to Airbus, are the greatest engineers in the world. They are the great practitioners of simplicity. Okay? Namely, they know how to build this. There is a book somewhere, actually I'm told there are 2 books, that tell you how to build this plane. What does that mean? That means I could take those books and give it to Guan Ying, and in principle, he could build this plane. In principle, because it's a formulae in some way. I'm simplifying a little bit, but that's what it is. So what they had done, in addition to that, they had created this extraordinary network of semi-autonomous entities that were feeding into making this all over the world. Look, there's Nagoya, Japan, Wichita, Kansas, Derby, United Kingdom, and so on, all coming together. Well, they hadn't realized that they had created a complex, potentially adaptive, evolving system with all of the problems, in principle even chaotic phenomena, I suppose, but all the potential problems of a complex system, not realizing that small effects somewhere here can have big effects elsewhere. And here's the result, which you you emphasize the business network part of it. Luis, you can correct me if I get my numbers wrong. When they built the plane, they needed to build, I think it was of the order of 300 to get a profit. After 300, you make a profit. They had orders of the order of 800, so it'd be great. 1 year delay, that number went from 300 to 600. Every delay has caused it to go further. Now, where it is now, and I know this because they not only have they told me, and I'm not breaking confidences, it was published in the Seattle Times. They now need to make 1,200 of these planes. So, my own editorial comment is, if this were a free market system, this company producing commercial aircrafts will probably go bust. So the word General Motors. Probably. So it's got huge business, you're exactly right. It has huge potential business implications. And just to emphasize that, the work that we're working on cities, and there's this little workshop on Thursday, and Luis will talk about much more about some of the stuff we're into. But an adjunct to that is in fact taking some of those ideas to ask, is there kind of a science of companies? You know, can you make, say, and that's much harder, but that's the kind of thing we're doing, and I think has potential impact, and that's why, you know, businesses need to be engaged.
Okay, well that was a long answer to one question, so this was the last question. Thank you very much, Geoffrey. We have a little token of appreciation. Is it's difficult to predict the future. This may help. Thanks once again.
Thank you. Thank you. That's all right.
That's all right.